So in this video, I'm going to be going through our notes on projectile motion. I'm then going through one example on how to use the kinematics and our knowledge on projectile motion to figure out some problems. So a little bit of review from the lab that you guys should have done virtually. The variables that do end up actually affecting motion of a projectile or its landing location are the angle you shoot it at. Right? If you increase the angle, well, if obviously you're flat, the object will go straight into the ground. So as you increase the angle, you increase the distance. But that's about until you get to around 45 degrees. And then after that, you are going to start decreasing the distance that we're going to, right? So angle does have an effect, but it's not necessarily just as you increase angle, you increase the distance, right? For some of these, it will be. Angle is obviously complicated, though. For height, if you change the height of that you're launching the object from, that obviously will increase the distance that the object goes, right? The farther up you throw the object, or sorry, the farther up the object is when it is thrown or shot, the farther the object will go. The initial speed, obviously, if the object is shot at 30 meters per second as opposed to just 2 meters per second, it will obviously go farther. And then the gravity, again, I feel like this one was pretty straightforward. As you increase gravity, you increase gravity, you decrease the distance the object will go because it will be pulled down quicker, right? Air resistance, if you turn on air resistance, obviously the friction will pull back on the object and mean it won't go as far. Things that I think might have surprised some of you that don't have an effect here. Mass. Mass does not actually have an impact on how far an object will go when it's shot via projectile. Diameter does not either. For this one, diameter does not if you turn off air resistance. If you do turn on air resistance, which is realistic to real life, the diameter would have an effect, right? Because obviously a smaller object going to have less air pushing on it, so it's going to have less air resistance. A bigger object is going to have more air resistance, therefore it will be actually affected. It will be pulled back a little bit. So the next one, because I know that some of you have an issue with this mass not having an effect on the projectile. A kid with a slingshot is trying to shoot a rock as far as possible. He finds that the bigger and heavier the rock is, the less far it will go. He concludes that the mass of a rock does affect how far it falls or how it falls to the ground. So why does the mass have an impact in this scenario? We really have to think back to Newton's second law for this one. Having more mass means that you have less acceleration if you're pulling with the same force. And in this case, if I pull the slingshot back the same amount, I'm applying the same force to those rocks, right? So if I have a rock that is less massive, and I apply the same force to it, it will have more acceleration, therefore it's going to go farther, right? If I have something that's more massive, then the same amount of force, the same amount of pullback is going to only accelerate it not as much, right? So it's going to accelerate less because it has more mass. But if you give them the same initial speed, then they would actually go the same distance, even though they have the same mass. One thing to also think about, sometimes, as like in this scenario, it says the bigger rocks, right? So at that point, we're changing diameter as well. So we're not only changing our initial speed, we're not only changing our diameter, but we're also changing our mass. So we don't know if our distance that we go is because of one of those three variables. The example I gave you guys to show that our initial speeds would be different is if we're pushing them with 10 newtons of force, one weighs 1 kilogram, it will accelerate at 10 meters per second. If you increase by 1 kilogram from 10 newtons, from 1 kilogram to 2 kilograms, you now do 10 newtons divided by 2 kilograms, and your acceleration is cut in half. Right? So obviously our initial velocity is going to be significantly less, meaning the object just won't go as far. Okay? So it's a little bit more complicated than just straight up. The more massive an object is, it will go less far. All right. Next, I want you guys to pause the video and describe the motion of a projectile in your own words. Right, a projectile is just an object flying through the air. Okay, pause. Describe it in your own words. So this should have been enough time. Once you pause it, just go ahead from this point on. Projectile is an object that is moving both horizontally, left and right, and vertically, up and down. So if I throw a tennis ball in the air, it will arc in the air and make that a projectile. Right? It lands in the other person's hand. So I was asked to represent this via velocity vectors, vertical velocity, horizontal velocity, and I need to also show the acceleration in each of these locations. So my red arrows are obviously my horizontal or left and right velocity, and notice that those are going to stay the same. It's going to go the same horizontal distance each time. My black arrows are my velocity vectors, vertical velocity vectors, and it decreases at first, comes to a stop, and then increases on the way down. Right, similar to how Wile E. Coyote was decreasing in speed as he went up, and then increasing in speed as he went down. Right, it's pretty similar because we have the same acceleration here, all caused by the force gravity, just going straight down on the object, accelerating it down to the earth the same amount at each location. Right? If you remember from the Wile E. Coyote thing, the only force working on that object was the force gravity pulling it down. We have no force pushing it left or right, so it's going to go at a constant speed left and right. And then for its vertical, it will slow down as it goes up and then speed up as it goes down. So you guys should have noticed some of those patterns, which I just kind of described here for you. But again, what patterns did you notice about the shape of the motion? It's like an arc, right? Like one half of the McDonald's logo. And then what patterns did you notice about the horizontal velocity? It stays constant or has zero acceleration. What patterns did you notice about the vertical velocity of the ball? It slows down as it goes up and speeds up as it goes down, meaning we have a negative acceleration. And then again, what is the only force acting or causing a acceleration on a projectile? In this case, in all cases, it's just gravity. Right? If we really wanted to include air resistance, we could, but that makes it a little bit harder. And honestly, the air resistance isn't going to be really significant in most of our cases. It's going to be so small. So the final thing I wanted to do is go through one example of using the kinematic equations to help us solve this problem. So the problem is you are throwing a ball off the table. It is moving at 5 meters per second when it leaves the surface of the table. If the table is 2 meters tall, so its height is 2 meters, what is the horizontal distance the ball travels? So in these problems, what I'm asking for is to not just list out these variables that we use for kinematics, but also that you list out them into separate vertical and horizontal components. Right? So for my vertical components, my height or my distance is 2 meters. Right? It's 2 meters up, so it needs to go 2 meters down. That's the distance it's going to travel. Well, I could have called it negative if I wanted to, but we're just going to leave it as 2. My initial velocity for my vertical object, right? It's not moving vertically at first, it's just going off the table, and then it starts to move vertical. So it's 0 is its initial velocity vertically. And then our acceleration vertically is just due to gravity. It's -10, right, due to gravity. I don't know the time, and I don't know my final velocity vertically. Horizontally, let's look at what we know. We don't know the distance it goes horizontally. That's what we're ultimately being asked for. We know the initial vertical velocity is 5. We know the acceleration is 0 because there are no forces acting on it as it goes through the air horizontally. I don't know the time. And then I do know that it doesn't speed up. So I know the final velocity, if it starts at 5, it ends at 5, right? So the trick to these problems is that you need to in some way connect the vertical and horizontal velocities. The way that we do this is the time, because the rest of them can be completely independent of each other. But for time, if I have an object that hits the ground vertically, that means it's also going to stop horizontally, right? So when I'm doing these problems, the time it takes for the object to hit the ground horizontally is also the time it takes for it to hit the ground vertically. So that's kind of how I'm going to do this, is I solve for time horizontally, and then I can use that time to figure out vertically. I figure out the time vertically, and then I can figure out the distance or the displacement horizontally. So I'm going to use just the vertical components over here, and I'm going to rearrange my kinematic equation, use the equation that I provided for you guys at one point, which is time equals the square root of 2 times the distance divided by our acceleration. So 2 times 2, which is our distance, or -2, either way, divided by 10, or -10, either way is fine in this case. So I get 4 divided by 10, I get 0.4. So the square root of 0.4, which if you plug into your calculator, your time then is 0.63 seconds. So that's how long it took for it to reach the ground vertically, right? Which I knew because I knew the initial vertical velocity and I knew the acceleration. I also had the distance it went. So now I have the time vertically, which remember is the same as the time horizontally, right? The final piece of this, I could use a kinematic because I have lots of information about my horizontal pieces now, but I'm going to use my knowledge on the fact that if the velocity is constant, in this case, again, horizontal velocity is constant, then my velocity is just equal to the distance divided by the time. So I rearrange that and I get the time times velocity gives us our distance. So I know its velocity is 5, I know the time is 0.63 seconds, so I just multiply those together and I get 3.15 meters. So again, this is just really using the kinematics. The difficult part is that I have vertical components and horizontal components. Please remember to always keep those separated when you guys are doing these problems, right? I shouldn't plug in my vertical displacement and then my horizontal acceleration. Make sure that as you're plugging them into an equation, you keep them consistent. These are all my verticals, these are all my horizontals, right? Please just give it your best shot as you're going through worksheet number 1, which is on the kinematics, and then worksheet number 2 will be more similar to this problem where you're looking at vertical and horizontal. Again, worksheet number 1 should just be a review on how we use the kinematic equations. All right, have a good day, guys. Let me know if you have any questions.